The Fujita Scale, where it all began. Our story starts in 1971 with Dr. Tetsuya Theodore Fujita, a Japanese-American meteorologist known as Mr. Tornado. He developed the original Fujita scale, F scale, which categorized tornadoes from F0 to F5 based on the damage they left behind. Dr. Fujita's idea was simple but revolutionary. Since direct wind speed measurements are nearly impossible during a tornado, we can estimate strength by observing what the storm destroyed. Here's how his scale worked. F0, 40 to 72 miles per hour. Light damage, tree branches broken, signs bent. F1, 73 to 112 miles per hour. Moderate damage, roof tiles lifted, mobile homes overturned. F2, 113 to 157 miles per hour. Considerable damage, roofs torn off, cars pushed. F3, 158 to 206 miles per hour. Severe damage, trains overturned, forests flattened. F4, 207 to 260 miles per hour. Devastating damage, strong houses leveled. F5, 261 to 318 miles per hour. Incredible damage, houses swept off foundations, cars thrown hundreds of meters. For the first time, scientists had a universal system to communicate tornado strength. Why the original scale needed an update? By the 1990s, engineers realized something important. Not all damage was caused by equally strong winds. Some houses were destroyed simply because they were poorly built, not because the tornado was extremely powerful. This led scientists to rethink the Fujita scale. It was a good foundation but needed more precision. Something that could factor in construction quality, structural integrity, and detailed engineering data. That's how the Enhanced Fujita scale was born. The Enhanced Fujita, EF scale, a more accurate tool. In 2007, the United States officially adopted the Enhanced Fujita, EF scale, designed by the National Weather Service, Texas Tech University, and several engineering groups. The EF scale refined Fujita's idea by adding damage indicators, DIs, 28 specific types of structures and objects that can be analyzed after a tornado. Each indicator has a degree of damage, DOD. For example, a house missing shingles might be EF0, while one missing its entire roof could be EF2. Here's how the modern scale looks. EF0, 65 to 85 miles per hour, minor roof or siding damage. EF1, 86 to 110 miles per hour, trees uprooted, windows broken. EF2, 111 to 135 miles per hour, roofs torn off, small buildings destroyed. EF3, 136 to 165 miles per hour, entire stories of houses destroyed. EF4, 166 to 200 miles per hour, well-built homes leveled. EF5, over 200 miles per hour, strong homes swept off foundations, pavement ripped up. This method allows for a far more accurate representation of how powerful a tornado truly was. Field surveys, the science of reading destruction. After every tornado, meteorologists and engineers rush to the affected area. They're not there just to document, they're detectives. Using drones, satellite images, and on-the-ground photography, survey teams map out the tornado's path, width, and intensity. They analyze each damaged building and piece of debris, noting how it failed. For example, did the roof lift off or did walls collapse first? Were trees snapped or completely debarked? Was debris scattered in a single direction or multiple? They record GPS points, take hundreds of photos, and assign EF ratings along the tornado's path, because strength often varies. One end of a tornado might be EF1, while another section could be EF4. Sometimes teams consult engineers to determine if a destroyed home met building codes. If it didn't, that damage can't be used to justify a higher rating. This ensures fairness and scientific accuracy. Radar and technology, seeing the invisible. While field surveys show what the tornado did, radar shows what it was doing. Modern Doppler radar technology measures wind speed and direction inside the storm. When winds move toward or away from the radar site, the frequency of the radar signal shifts slightly. That's called the Doppler effect. This helps meteorologists spot rotating air, the signature of a tornado, even before it touches down. In extreme cases, radar has measured wind speeds exceeding 300 miles per hour within a tornado. However, radar can't officially determine EF ratings because it measures winds high above the ground, not where the actual destruction happens. Still, radar data is vital for issuing tornado warnings, saving countless lives every year. Path, width, and duration, the bigger picture. When measuring tornado strength, experts don't just focus on wind speed. They also record three critical metrics: path length, how far the tornado traveled on the ground; maximum width, how wide its damage path became; duration, how long it stayed on the ground. The 1925 Tri-State tornado remains the longest-track tornado in U.S. history, traveling over 219 miles and lasting about 3.5 hours. Even with primitive tools back then, scientists estimate it was an F5. The El Reno tornado in 2013 set a record for the widest tornado ever observed, 2.6 miles wide. Though it only lasted about 40 minutes, it caused catastrophic damage and tragically killed several storm chasers. Path length and duration help researchers understand how a storm evolved, while width shows how widespread the destruction was. Debris and secondary evidence, clues in the chaos. Every piece of debris tells a story. Where it lands, how it's twisted, and what it hits can reveal the tornado's power. For instance, when investigators find tree trunks stripped of bark, it's usually a sign of EF4 or EF5 winds. When steel beams bend like paper or heavy vehicles are thrown long distances, that's another indicator of violent intensity. After the Joplin, Missouri EF5 tornado in 2011, debris was found more than 300 miles away in Illinois. Light objects like paper and photos were lifted into the sky by powerful updrafts and carried across multiple states. These small discoveries help confirm just how far-reaching and complex a tornado's behavior can be. Engineering lessons. Learning from disaster. Every major tornado teaches engineers something new about building resilience. After the devastating 1999 Moore, Oklahoma tornado, experts studied why certain houses were obliterated while others nearby still stood. As a result, cities in Tornado Alley have since updated building codes to include stronger construction standards. What we learn from one disaster helps prevent future tragedies. The EF5, nature's most extreme rating. EF5 tornadoes are extremely rare, representing less than 1% of all recorded tornadoes. But when they strike, the destruction is beyond imagination. And EF5 doesn't just damage, it erases. Homes are completely swept away, foundations scoured clean, and the landscape itself often altered. Even well-built structures stand no chance. Some of the most infamous EF5s include Joplin, Missouri, 2011. 158 deaths, one of the deadliest modern tornadoes. Moore, Oklahoma, 2013. Winds over 210 miles per hour, thousands of homes flattened. Greensburg, Kansas, 2007. The entire town was nearly wiped off the map. When scientists study EF05 damage, they're not just rating destruction. They're documenting history's most powerful forces. Beyond the EF scale, the future of tornado. Measurement meteorology continues to evolve. Researchers are now experimenting with mobile radars, AI analysis, and drone surveillance to gather more precise data on tornadoes in real time. Projects like Vortex and Taurus send teams directly into storm systems with specialized instruments that record air pressure, wind speed, and temperature changes. The goal is to one day measure a tornado's power before it touches the ground, potentially predicting EF intensity in advance. Imagine knowing not just that a tornado is coming, but how strong it will be. What tornado damage really teaches us. In the end, measuring tornado damage isn't about numbers on a scale. It's about understanding chaos to save lives. Every destroyed home, every snapped tree, every scar across the land adds to our knowledge of how nature works. The EF scale isn't perfect, but it's the best tool we have to translate destruction into science. Each EF rating, from 0 to 5, tells a story about resilience, vulnerability, and the never-ending human effort to face the world's fiercest storms.